Hi everyone, welcome to our presentation of our paper Goal Recognition as Reinforcement Learning. This paper was published on AAAI this year. So in PRL, we are presenting an abstract of it, and you're welcome to take a look at the whole paper from AAAI. And in the next 5 minutes, I'll try to give you a brief overview of what our paper is all about, hopefully enticing you to read the full paper. So for starters, let's know what the problem is, right? So the motivation here is that we are trying to help solve goal recognition, and goal recognition is this task of trying to infer what is the ultimate goal of an actor that we are observing, right? Based on observations of the behavior of this actor, right? And ultimately, this is to decide what is the goal that best explains a sequence of observations of this actor's actions. So, I mean, we are trying to infer what is the home, right? Where is this actor's home, for example, based on the path this actor is taking, right? And we might not see the whole observation. We might get noise on the observation. So that's when the problem becomes interesting, right? And so this is related to a problem called plan recognition, which is kind of the origin of goal recognition. And in plan recognition, we try to recognize the plan, and if we get the entire plan, by extension, we can infer what the goal is, right? And this is one form of the problem of abduction, right? We try to explain why what I observed is the way it is, right? And most approaches to goal recognition, they rely on specifications of environmental dynamics. And because we need the specification of the environmental dynamics, we have a lot of limitations, right? Basically, the cost of getting this environmental dynamics, susceptibility to noise if the environment is noisy, and the costs of doing the recognition online. And so what we try to do is to employ RL-based approaches to try to address this limitation. And so basically what we want to do is to get a policy or a value function we obtain using model-free reinforcement learning, right, to process the observations and infer a goal. And we found out that by using very basic methods from RL, we can do very efficient and noise resistance goal recognition without the need to handcraft a domain model, right? And so the contributions of this paper are threefold, right? We redefine goal recognition to accommodate this idea of RL-based domains, right? We instantiate our framework for goal recognition based on reinforcement learning, so the first formulation of it, and we evaluate these techniques on domains with partial observability and noisy observability. And so goal recognition more formally, right, is that given a domain theory, a set of possible goals, the goal hypothesis, and a sequence of observations, we want to output which of these goals, right, is the goal that the observations explain, right? And so this is from Ramirez and Gaffney, or plan recognition as plan. So we might have various candidate goals, and we have an observation, and we want to say, well, which of the goals that our observations explain? And the limitations of the traditional approaches are not only limited to the domain, but to the fact that they use deterministic environments. Some approaches do allow for MDPs, but as we all know, it's much harder to model stochastic environments by hand than it would be to model, for example, PDDL for a classical domain. And reinforcement learning algorithms then allows us to build these informative functions describing the agent's preferences, which is basically what a policy is and what implicitly what a Q table or a value function are, right? And so they basically describe to us the expected return depending on which one of the reinforcement learning frameworks you choose, right? And so what we do is we replace that idea of a domain theory, that static idea, with a utility-based domain theory. And basically this, we assume we have the Q functions, right? So we have the Q value functions, or one based on a policy where we just have stochastic policies. And using this definition, we basically subsume the goals into this set of Q values or policies, right? And we just had the domain theory, the observations, and we want to output the goal. And by goal here, we mean one of the Q functions or one of the policies that generated the observations that explain that. And basically our approach has two stages, like learning and then inferring, right? And that's very simple, and I urge you to look at the paper for more details. So we basically learn policies using your favorite uh, reinforcement learning algorithm. And then given the policies or the Q-value functions, we use various methods of distance and of the divergence and whatnot to infer a goal. And that's basically it. So our work paves the way for this new class of goal recognition approaches, right, based on model-free reinforcement learning. And we want to improve the distance measures we are using function approximation, for example, neural networks, right? Our instantiation use tabular Q-learning, but it basically works, right? And the way we use that doesn't prevent us from replacing the Q tables from a function approximation, right? And you'll see that our experiments are based on PDDL, basically because that's where the data sets are, right? And also, including in using function approximation, we are working on image-based domain rather than symbolic PDDL ones. And that's basically it. Check out the paper, and if you have any questions, I'm here. Thank you very much.